Alright, so as I promised, we're gonna go ahead and look into word problems today. So, unlike your usual word problems you encountered in the past few units, those word problems were very easy, very straightforward, and as long as you really knew what functions were and you knew all the concepts inside of that unit, you should be able to do all fine on the word problem questions. However, it's not the case for this. Um, this unit actually has word problems that are a little challenging. And some of these word problems, they are they're ideal. They're in an ideal case. An example that I want to go ahead and talk about right now is that let's say we have this bouncing ball that every bounce is gonna lose some of its power, and eventually it's gonna stop bouncing, right? Because obviously it's gonna lose all of its power, and there's gonna be no more forces left for it to continue bouncing. However, if we have a mathematical equation, we really can't do anything about it. Because whenever we have that mathematical equation, we're going to approximate it by, how high it will bounce the next time by a geometric sequence. We're going to do like, let's say, originally it bounces 4 meters and then it diminishes to, let's say, well, one half every time. So that's going to, let's say, four times one half to the whatever power. Let's write it out. So 4 times 1/2 to the nth power. However, you will essentially realize that this thing is never going to be zero. So, but that's impossible because the ball will essentially stop bouncing out, any time. And if you do that in real life, it actually conflicts this mathematical equation, and that's because we're not encountering a lot of other factors inside of this. For example, we're not encountering we're actually going to lose some gravity here and there. And because we are also releasing gravity and the ball is also releasing some sort of gravity, it's essentially going to burn out and it's going to have no more forces left. We're probably going to go through one of these examples later in the geometric sequence one, which really isn't going to do anything with our arithmetic. Let's go ahead and do the arithmetics. So find the common difference for the sequence whose formula is this. Just write out the terms. For 1, that's just -1. For 2, that is just 1, and for 3, that's just 3. So the increment is 2, so obviously our common difference is d equals 2. And that is our 12. For 13, it's pretty easy. So basically, A, we have 14 something 26. So this is an increase by 12. So because that's every other number increases by 12, it means every number we increase by 6. So essentially the middle number is 20, and our entire sequence should look something like 14, 20, 26, 8, and 2. B is pretty much the same thing, and you just have to do that yourself. Very simple. And let's go ahead and do 14. So, the modern Summer Olympic Games were first held in Athens, Greece, back in 1896. And these games are held every 4 years, which should be common knowledge for most people. But we can turn this into an arithmetic sequence because every 4 year we're gonna have a year that we have an Olympics game. So essentially, we're gonna have 1896 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4, and then that's gonna be the entire thing. Let's go ahead and write out what A and D is. So A, obviously, it's 1896, and D is obviously 4 because we're adding 4 every year, every time, and every 4 year there's gonna be an Olympic game. Pretty straightforward. So let's go ahead and see. B is a research question. In what years were the games cancelled? So in history, there were actually 3 games. That'd be 1940, 1944, and 2020 because of pandemic and World War II. So let's go ahead and take 1940 as an example. So let's go ahead and do C. What are the term numbers for the years cancelled? So we don't know what term it is. We don't know what term it is. So Tn is equal to 1940. So why not? Why not? We could do what we could have done 1944 or 2020. I highly suggest you take these years as practice and do it on your own. But I'm just gonna do 1940 as an example. So let's go ahead and remind ourselves what our arithmetic sequence formula was. That was T equals A plus n minus 1 plus multiplied by D. Right? That was our entire formula. So our Tn, we know our Tn is 1940. And we know A is 1896. And we're adding n minus 1, and we know D is 4. D is 4. Let's go ahead and expand the right side. Okay, actually, no. Let's go ahead and move this to the left side. So 1940 minus 1896. It's going to go ahead and give you 44. And that's going to give you, and it's equal to, let's go ahead and expand this. So 4n minus 4. So let's go ahead and move this here. So that's 48 equals 4n. And obviously 48 divided by 4, that's going to give you 12. So with our math, we can figure out is the 12 Olympic that got canceled. So pretty straightforward. And I recommend you to practice for where Tn is equal to 1944 and Tn is equal to 2020. So I would recommend you to do this because obviously this is the 13th because we already figured out that 1940 is the 12. Pretty simple. So what is the term number for the next summer games? Yeah, 13, and it's pretty easy. How many multiplies of 5 are there from 15 to 40 inclusive? So, multiplies of 5. So, I would assume that it's copies. So, in 15, there's 3 copies of 5. And in 450, and let's say, oh, so multiplies from 5. Okay, so 15 is 1. 20 is 1. And, so basically, every 5, there's gonna be a multiply 5. So, A is 15. And the common difference is 5. Let's go ahead and calculate the total number of terms. So Tn is actually 450 because that's our last term. And it's equal to 15 plus n minus 1 times 5. Let's go ahead and solve this. So 450 minus 435 equal to 5n minus 5. So 440 equals 5n. Let's just divide. 440 divided by 5. It's going to give you 88. So n, there's 88. So there's 88 terms. 88 terms from 15 to 245. So essentially 450 is the 88th term. So that doesn't include 15. You might have noticed that because it said inclusive for a reason. So essentially you're gonna give your answer as 89 plus 1. 89. All right. So 89 multiplies our 5. 18th, 16. The 18th term of an arithmetic sequence is 262. Common difference is 15. What is the first term of the sequence? Again, let's plug in the formula. So Tn, the 18th term. So 18th term is 262. It's going to equal to A. Let me write at the bottom. More space. 262 equals A plus, we know n is we know it's the 18th term. So 18 minus 1, 17d. 17d. Now common difference is 50. All right. So that's just literally a linear algebra question. 17 times 15, that's 255. 262 minus 255, we know that A equals 7. right? And the rest of the questions are pretty easy. Barrie is 60 kilometers north of Toronto by road, and blah blah blah. All of this. So these ones are pretty easy. And I'm all right. Quick break, and we're back into this geometric sequence part. So very straightforward, even more straightforward than arithmetic actually. So each year for 10 years, the population of the city increased by 5% of its value in the previous year. If the initial population was 200,000, what is the population after 10 years? Very easy. T n is just equal to 200k multiplied by 1.05 to the power of 10. And then after you multiply that out, 1.05 to the power of 10, it's just 1.62.88. And then there's a long number followed by it. And then we multiply that by 200,000. And our final value should be, which is rounded, 325,779. We got the same answer. And each stroke of a vacuum pump removes 1/3 of the air remaining in the container. What percent of the original quantity of air is remaining in the container after 10 strokes to the nearest percent? Let's go ahead and do that. So if we remove 1/3 every single time, that means 2/3 is going to remain. So let's say we have 100% at the start. So 100%. Every stroke is going to remove 1/3. So it's going to have 2/3. And this is to the 10. So 2/3 to the 10. That's going to give you 1,024 over 59,000 and over 59,049. It's going to round to a percent of 0.017341. So 100% multiply that is actually 1.7314341%, which rounded to the nearest percent will go ahead and give you 2%. Hope you got that right. Okay. Many photocopiers can reduce the dimensions of the image of an original. Usually, the maximum reduction that these machines can do is to the 64% of its original dimensions. So, how many reductions at maximum setting would it take to reduce an image to less than 10% of its original dimensions? So essentially what we're trying to do is 0.64. So how many 0.64 to the n power we are going to need so it's less than 0.1, which is 10%. So essentially we know how to do this back in the days of solving exponential functions. We do this. N log 0.64 less than log of 0.1. So we solve for n. Essentially n is gonna so basically we divide both sides. However, we will realize that both of these are negative. This is a negative. This is negative, and this is also negative. So negative over negative, essentially we will have to flip the signs. So n is going to be greater than log 0.64 over log 0.1, which in this case, log 0.1 is actually just -1, so -1 over log 0.64. It's going to go ahead and give us an approximate answer, which is 5.16. So since n has to be greater than that, and it has to be a whole number, we'll just do n equals 6. Right? So this bare minimum, 6 reduction is needed for it to go down. Bare minimum. Okay. Now let's go ahead and do this. 13. Biology. A single bacterium divides into 2 bacteria every 10 minutes. If the same rate of division continues for 2 hours, how many bacteria will there be? So originally we start at 1. And then every 10 minutes it goes to 2 and then blah blah blah. So, let's see. Bacteria doubles every 10 minutes. So let's see how many minutes are in 2 hours. 120 minutes. So that means there's going to be 12 divisions. And since this little bacteria doubles every time, our equation should be 1 times 2 to the 12. So now what is 2 to the 12? 4,096. So after 2 hours, there's going to be 4096 bacteria present. The 14th, the first 14, the first two terms of a sequence is 3 and 6. If the sequence is arithmetic, this is going to go ahead and give us 3, 6, 9, 12, 9, 12, 15. Because we add 3 every time. Now, if the sequence is geometric, it will be multiplied by 2. So that will be 3, 6, 12, 24, and 48. Right? Very, very, very straightforward. We're not going to graph that because I don't want to pull out decimals. But it's very easy to graph. Which term of geometric sequence 4, 12, 36 is 2916? Okay, so now we actually get into geometric sequence. Let's go ahead and write out the entire formula. So we know that the first term is 4. So Tn is equal to 4. Our common ratio is obviously 3. So let's see. Tn. So we know the term is 2916. 2916 is equal to 4. So let's we know first step. Let's go ahead and divide that by 4, which is going to give us 729. Is equal to 3n over 3's. Right? So 729 times 3, 2187. And so what power of 3 gives you 2187? We know it's 7. So 3 to the 7 is going to give you 2187. So let's just write n equals 7. So we know the seventh term of this geometric sequence is 2916. Now let's talk about some real life application questions. So obviously, if you took any single biology or chemistry or physics or any single class of grade 11, any science class, or even I think economists, yeah, probably accounting, they let you do I think, yeah, there's accounting questions where it talks about the value that is essentially is gonna inflation and deflation rate and all of that, and you will know that a great type and a very very obvious type of geometric questions is radioactive decay or radioactive increase, doubling, whatever. So let's go ahead and do one of these. The rate of decay of a radioactive for a radioactive isotope varies from one isotope to another. So the time it takes for half of any sample to decay is called half-life. So barium 123, which is the number, the atomic number. So the barium 123, which is an isotope, has a half-life of 2 minutes. So essentially, for every 2 minutes, it's gonna go down by half. So originally, if I had 100% after 2 minutes, 50% after 2 minutes, 25%. Very, very, very straightforward. So write an equation to determine the quantity of barium 223 remaining in sample after n half-life. Right away, let's go ahead and do f at n. Okay, let's do t at n because time at n, which is any time, and is gonna go ahead and equal to. So for the initial amount, let's just not use anything unfamiliar. Let's still use a. That's the initial amount. So a, and then obviously it has every n. And B is we're gonna plug in some real numbers. A fresh sample of 80 milligrams of barium 123 was obtained from an experiment. It took 10 minutes to set up the experiment. So what mass of barium 123 is left after when the experiment began? So 10 minutes has run. So basically, excuse me. So let's do this. So Tn, 10 minutes, and our A was 80 milligrams. and we're gonna do 1 to 1/2. However, we look at n, and we're like, what is this? It's 2 over 2 minutes, right? So we forgot to write that. So 10 over 2 is 5. So 1 over 2 to the 5th power is actually 1 over 32. That's just some exponential law that you should know. So this is 1 over 32. 80 over 1 over 32 is going to go ahead and give you 2.5. So as we know, we can therefore write a conclusion statement. After 10 minutes, only 2.5 milligrams of barium-123 is left in the sample. And that is all the example that I want to do for these sequence questions. Overall, they are still very straightforward. However, just like this one, essentially in real life, there's gonna be a point where this barium-123 is just gone. And however, in mathematically, it's never gonna happen because there's always gonna be a value for it. So this is something you're gonna learn in calculus in grade 12. Is that essentially when as a point, if a point continues to reach 0, let's say I have a value so small, so small as 0.0000000000001. Instead of taking it as an actual value, we're gonna go look at it as a 0. However, that's something for your grade 12 teachers to tell you. And these are some more practices, and that's it for today's class.